So in this video, I'd like to discuss how to minimize a finite state machine. And what that means is if I were to give you a finite state machine, for example, I want to be able to reduce that finite state machine in order to use the smallest number of states possible. There are many reasons why we might want to do this. You know, perhaps the biggest reason why we might want to minimize our finite state machines is because it will limit the amount of gates and flip-flops, the amount of logic that we need in our circuit in order to implement the finite state machine. So we always want to make things smaller. That's going to make things cheaper and faster. So I'm going to show you two methods of minimization in this particular video, right? So first, let's take a look at a finite state machine. Here is a finite state machine that's been given to you. So we can see that I start in state S0 over here, and I can proceed right along to S1 and S3 from there, and then eventually I end up in S2 or S4, where I kind of get stuck, right? I can't go anywhere else from S2 or S4. Once I'm in those particular states, I'm just stuck there forever. This finite state machine, I don't believe, has any specific purpose. It just is a finite state machine that I made up for this particular example. The first way of minimizing this finite state machine that I would like to talk about is trying to identify similar states. And so the way that that works is you take a look at all states that share the same outputs. So in this particular case, state 0, state 1, and state 3 all output a 0, right? State 2 and state 4 both output a 1. So if they don't output the same value, there's no way the states can be the same, right? There's no possible way the states could be condensed together. But if they do output the same value, then we can then look at potentially condensing them down, seeing if they are in fact identical states. And so if I look at this particular state machine, I see that in state 1, right, I have 0, 1, 0 leading to state 2, and I have 1, 0, 0 leading to state 4. And then if I look down here at state 3, which also outputs 0, I have 0, 1, 0 also leading to state 2, and 1, 0, 0 also leading to state 4. So in that particular case, there is nothing distinguishing these particular states. These states are in fact identical. They lead to the same place based on the same inputs, and they also output the same value. That's how we can determine if two states are identical to one another. So then the question becomes, what do I do with the inputs to these particular states? So I'm going to eliminate one of these. I'm going to eliminate S3 in this particular case, although I just as easily could have eliminated S1 if I had wanted to. It wouldn't make any difference as far as the minimization process is concerned. But I'm going to eliminate S3, and so the arrow, the transition that's pointing to S3 from S0, now needs to point to S1, which is what we are saying is an identical state to S3. And so once we do that, here's what our finite state machine looks like. You can see that I've just included a second set of inputs on this transition that can lead to S1. I've eliminated S3 entirely. In fact, I indicated that S1 and S3 are now the same by changing the name of this particular state. And we are now down to 4 states, whereas previously we had 5. So we can actually do a little bit more with this finite state machine in terms of minimization. If I take a look at these two states, state 2 and state 4, I see that they both output 1s, right? And I see that there's no other transitions out of these states than these self-transitions, the transitions that go to the same state that we're already in. And if you notice, these self-transitions operate on the same set of inputs, right? So even though these don't go to the same exact state, I can still say that state 2 and state 4 are equivalent because the self-loops also have identical inputs. And of course, they share outputs as well, which is another condition for saying that two states are identical. So this is kind of an exception to our original rule that says they both must transition to the same states. The exception is self-loops. If the self-loops has the same transitions, right, for each state, then I can also minimize those particular states. I can also condense them. So state 2 and state 4 are identical. Again, I need to take a look at what I do with the transitions into state 2 and state 4. I'm going to eliminate state 2 in this particular case. Of course, I could have eliminated state 4 as well if I wanted to, but I'm going to eliminate state 2, which means that this transition from state 1 to state 2 now has to go to state 4 instead. And so what we end up with is this. This is our final minimized state machine. We started with 5 states, and we ended up with 3. If you take a look, right, you can try to condense. The only other thing that we could even attempt to condense is state 0 and state 1, since they share the same outputs. But we cannot do that for the reason that the transitions here, even though they are identical, they do not lead to the same states, right? They do not lead to the same results. So we cannot simplify this anymore. We cannot minimize this state diagram any farther than we already have. So that's one technique of minimization, is trying to identify identical states and combining them together. I'm going to show you now the second form of trying to minimize a finite state machine. Here is our original finite state machine again, right? The second way of minimizing a finite state machine says, find all of the states that have the same output. So in this case, I have these 3 states, state 0, 1, and 3 with the same output. I have state 2 and 4 with the same output. And we are just going to assume, right? We're just going to assume that I can represent all 3 of these states with 1 state, and I can represent both of these states with 1 state. So I'm basically going to combine all of the states together that share the same output. And I'm not going to include the transitions just yet. We're going to worry about the transitions later. So once I combine these states together, here's what I end up with. I have states 0, 1, and 3 all in 1 state because they share an output of 0. And then I have states 2 and 4 also condensed into a single state. And now what I want to do is take a look at each of these combinations. I want to take a look at each of these states individually and see if I can find, right, a reason to split these values up. So in other words, I want to take a look at S0, S1, and S3 and see if I can find a transition out of one of these 3 states that does not match the same transition out of another one of these 3 states. So since we've already done this example once, right, we already know what that transition is going to be. If I take a look at state 0, for example, I transition on 1, 0, 0 to state 1 and 0, 1, 0 to state 3. But state 1 and state 3 on 1, 0, 0 transition to state 4, which has a completely different output than state 1 and state 3. Therefore, state 0, state 1, and state 3 cannot be the same state. We must split them apart. And so that would look something like this. I now have 3 states, right? State 0 cannot be merged with state 1 and state 3. So now we would take a look at our remaining combinations and see if we can split them apart. So I'd take a look at state 1 and state 3 and see if I can find a transition, right, that leads to different states from each of these smaller states. And I can't. I actually can't in this particular case. The transitions both lead to the same place. And the same thing is true of state 2 and state 4, right? The transitions lead to the same place for the reasons that we discussed. So at this point, we are finished splitting our states apart. And now the final piece is to add in the transitions, which we can do by referring to the original diagram. And so what we end up with is the solution that we see on the screen here, which, if you notice, is exactly the same solution that we ended up with in the previous method. So that about sums it up for minimization. Just to recap, there are 2 ways to minimize a finite state machine. I can start with the original finite state machine and try to merge states together until I can no longer merge states together. Or I can try the opposite approach that says merge all of the states together at the beginning and then try to split them apart until I can no longer split the states apart. Neither approach is necessarily better than the other, but you should definitely practice using them both and see which one makes the most sense to you.